About gamma ray bursts and the possibility to use them as in cosmology. The point of view of my talk is extremely observative, and in the outline I start with a kind of introduction for those of you that are not working on gamma ray bursts, just trying in a few slides to define these sources. I should work, but it doesn't. So, here we go. So first I will introduce gamma ray bursts, and then I will enter into the possibility to use these sources to constrain some cosmological parameters or to do something else in cosmology. The first point is how to define a gamma ray burst. We know these sources since, I would say, 35 years or so, and we use this nomenclature. We call the prompt emission the high energy emission from these sources, which are quite short in duration. When I say prompt emission, I mean photon energy is above a few tenths of keV, with a typical, let's say, duration which can range from a few milliseconds up to a few kiloseconds. And the prompt emission, as you see in this example, is highly variable, with a typical variability time scale of the order of a few milliseconds, therefore highlighting the possibility that, for causality reason, the object which is at the center of these sources and which is powering these sources is something like a compact object. We know since 1997 what is the emission of these sources at lower frequencies. In fact, it was discovered in 1997 that the so-called afterglow emission is the emission coming up at lower frequencies in the optical, in the infrared, in the radio, which can last much longer than the prompt one, hours, days, and months, and which is typically very smooth. Here you see how it decays in time, following, for instance, two different decay slopes, flatter at the beginning and faster later on, as a function of time. So these are the two main components, roughly speaking, of these objects from the observational point of view. The common feature of, I would say, the prompt and the afterglow emission is that the spectrum looks almost, I would say, non-thermal. Surely for what concerns the afterglow emission, maybe for what concerns the prompt emission. By considering large samples of gamma ray burst, it was early discovered in the 90s that if you plot the duration distribution of these sources, they end up to be divided or divisible into two categories. The short ones, which have a duration, let's say, in the observational frame smaller than 2 seconds, and the long ones. This was the first hint of the possibility that these two gamma ray bursts divided by their duration might have a different origin. Another piece of this possible idea comes from the fact that if you consider the hardness ratio, basically some indicator of the hardness of the spectrum of these sources, and you plot it as a function of the duration, you see that short bursts have a harder hardness ratio with respect to long ones, therefore suggesting that they might have a different origin. This is not an exhaustive introduction, but it's something I want to do to come to this point. So what is the current idea about the origin of this cosmic explosion? The current paradigm, I would say, is the fact that we think that short gamma ray bursts can be produced in different scenarios, but they all have in common the fact that there must be a kind of merger between two compact objects. And there are different receives, double neutron star, black hole neutron star, black hole white dwarf. Whereas for the population of long gamma ray bursts, which stands in the ratio of one short every, I would say, 4 long gamma ray bursts. So for long gamma ray bursts that are 4 times larger in number in frequency with respect to short, the idea is that they are produced by the core collapse of very massive stars at the end of their lives. This is the so-called collapsar model. This is what is the progenitor of the gamma ray burst, but how the emission happens. This is the so-called standard picture that we have for these sources. So the common feature of either the progenitor of short gamma ray burst being produced by the merger of two compact objects, or the progenitor of long gamma ray burst being the result of the core collapse of a massive star, is that in the end you form something like a black hole with around an accretion disk. The extraction of energy from this system, which is quite common in astrophysics, powers a kind of jet. We could discuss about the the nature of this jet and the nature of the outflow, either magnetically dominated or matter dominated. But in the standard picture, what it came out, or what it was proposed originally, is that it is matter dominated. So basically what you have is a kind of outflow in which the energy is quite large, as you will see in a moment. There are a few baryons, and especially at the base of the jet, the opacity is so large that everything is opaque. So the photons which are trapped within this outflow are pushing an accelerated expansion, so that you very easily, in this phase, which is called the acceleration phase, you increase the Bartholin's factor of the ejecta up to a point at which, due to the increase of the size, the optical depth decreases below unity. At that time, you reach transparency. The photons which were pushing the acceleration before are now free to escape, and therefore you enter in a so-called constant velocity expansion phase. In this phase, what happens, if you imagine that the emission of this outflow is not something very regular, but it's somehow erratic, you might think that different parts of the outflow, which are moving with different smart velocity, can collide one with the other. The collision, therefore, is the mechanism which allows to reconvert the kinetic energy that this kind of outflow acquired in the acceleration phase into electromagnetic emission through the formation of shocks and the acceleration of particles there. However, these collisions here, which are called internal shocks, are not that much efficient because they are made by things that are moving with slightly different Bartholin's factor, and most of the energy is conserved and it is dissipated farther out when this outflow is decelerated by the interstellar medium. This happens at a so-called external shock, and the radiation process is the same, it is thought, of the internal shocks, but the emission there is at lower frequency, and it's a typical emission due to the deceleration of this kind of fireball, and therefore can explain the decay of the flux that you see in the afterglow phase. This was the introduction, maybe too fast, but I hope I gave a few information. Let's put now gamma ray burst in a cosmological context. We know, since I would say 10 years or so, that gamma ray bursts are cosmological sources. And for many of them, not all of them, a fraction, but somehow an increasing fraction, it was possible to measure their redshift and therefore infer their distance and also their energetics. Why gamma ray bursts are interesting from a cosmological point of view? Because already now they are extending in a redshift range where they could represent an important probe of the properties of the universe. Here I just put a burst, which I will show you just a picture later, which is a very recent detection of this burst. It was detected on the 23rd of 2009, and it seems to be, quite surely, a source which is at redshift 8.2, which is really high. And why is that important? Because, well, you can infer many things. First of all, if gamma ray bursts are originated by stellar explosion, you must think that stars, or some kind of stars, should be already in place there at that redshift. And the other possibility is that if you use gamma ray bursts as background illuminators, you can use them to infer properties of the IGM. So there are many applications that could be done. I would say that we are at the beginning in this field, as far as it is very difficult to make high-resolution spectroscopy of these very distant sources. But these are the things that can be done or could be done with gamma ray bursts. The main advantage of gamma ray bursts with respect to quasars or to quasar cosmology is the fact that I would say they have the advantage that being transient sources, they do not suffer many proximity effects, in the sense that their strong sphere is very limited to the region where they explode. Therefore, they can allow you to probe the properties of the medium inside the host galaxy of the gamma ray burst. The other point is that their spectrum is quite clean, and the most important thing is that being sources that are detected in the gamma ray, they allows you to select a bias of galaxies at very high redshift, or as a function of redshift, which is not biased by the typical optical searches. So they sign spot the galaxy beacons, if you want, if you go to very high redshift. This is what could be done, but now I would like to enter into another possible application of gamma reversed in cosmology, which is also a possibility. It's not a fact, but I think it's quite intriguing. First, let's start with the redshift distribution of these sources. Here you see a quite old plot, I'm sorry, I should update that, which contains 104 gamma reversed. I think now we have, with measured redshift, and now I think we have something like 130 or something like that. It is not updated because here the redshift, the largest redshift was at redshift 6.3, then there is another one at redshift 7.2, and then the last one detected at redshift 8.2. But as you can see, the redshift distribution is roughly peaked at redshift 1, with the median redshift which is a bit larger. Now for these sources, in the gamma ray band, you detect and you measure the flux, or if you want, you can measure an integral measure of the flux, which is the so-called fluence, which is basically the flux integrated of the duration of the burst. And the typical time integrated flux, so the fluence, is in this range, in the, let's say, 1 keV, 10 MeV energy range. If you assume that these sources are emitting isotropically, you can build up this plot in which you see the so-called isotropic equivalent energy as a function of redshift. And there are many things that could be discussed about this plot, but the thing I would like you to focus on is the fact that, as you can see, in the extreme top of the distribution of the isotropic equivalent energy, there are sources, there are gamma reversed, that have an equivalent isotropic energy which is quite large. Especially if you consider this scale here, which corresponds in a way, for instance, for these sources here, to the conversion of roughly even up to 1 solar mass into energy, and on time scale, which is the duration of the prompt phase, which is, as I told you, of the order of few seconds, few tenths of seconds, few kiloseconds. So this is a challenge, if you want, for any machine that can release such a huge amount of energy on a short time scale.
What's the difference, blue and red
Pardon?
in the top panel? Just all Swift and the others?
Pardon?
In the top panel,
Yeah.
what's the difference? Blue points and red points?
No, it corresponds just to the division that I did on this plot, because I wanted to see, and in fact there is a kind of systematic effect for Swift burst. So those measured, detected by Swift starting in 2004 to, let's say, detect on average higher redshift burst. So this is just the reason why.
So still they call the borders press Swift level? Or
yeah, the red points are press Swift, the blue points are
high
Swift.
ones.
Yeah, this, you mean this point here? Yes, it's press Swift. It's 990123.
Can I ask you, this, why Swift detects high redshift? Just because Swift has low energy trigger, like compared to BETSI?
Yes, this is probably the main reason. There could be other reasons related to the fact that the pre-Swift redshift catch was limited. I will say something maybe later. Was limited by the fact that you had the position of the source, an accurate position, with a delay of the order of few hours. So with Swift instead, you get it immediately, and it's much easier also to take a spectrum while the source is still very bright. So this could explain in a bit the fact that you can make the redshift also for much higher redshift burst. Okay. But the fact that instead the low energy threshold arrives to 15 keV is what maybe is biasing most, the fact that you can catch up bursts which are softer.
Does it then mean that there is a cosmological evolution? In the sense that they are not standard candles, right? That there is something interestingly different in the spectra of gamma reversed at larger redshift than local?
Well, it could be, yeah, it's a correct question. I think that there are no hints, however, as much as we can test of a strong cosmological evolution of these sources.
No, but this redshift distribution itself is not the indication for this?
Well, not, because it's true that with Swift you catch the softest, but you're missing the hardest events. I mean, Swift is triggering with it's catching bursts, which on average have a peak energy, or most of their energy, the peak energy of the nu, so where most of the energy comes out, between 15 kV and 150 kV. So you are, in a sense, observing the low, or either the soft population of burst or the high redshift one. But you cannot conclude on the fact that, I mean, you are never observing a complete sample of sources in order to make that. But there are, however, you can do that with the largest population of Bazzi burst, and you can try to build up the luminosity function and make some tests for the cosmological evolution. And there are different results, but I think the present feeling is that there is not a strong cosmological evolution, or it doesn't appear for the data we have. Okay. So let's come to the spectrum. I introduce a new ingredient here, which is the fact that when you take the nu representation of the spectrum of a gamma ray burst, this is an example, it has typically a peak, very often, not always, it has a peak, which, for instance, as far as we knew from the Compton Gamma Ray Observatory, was at about 300 keV. This is the energy at which most of the photons from the source come out. If you take the integral of this spectral shape that you can model in some ways, you can derive what I showed you before, which is the isotropic equivalent energy, provided you know the redshift of this source. And the question here is, are these two measurements of the typical characteristic energy and the total energy emitted by the burst connected somehow? And it was found in 2002 by using 11 Beposac's gamma ray bursts that indeed the rest frame peak energy, so the rest frame energy at which the spectrum in nu peaks, and the isotropic energy of this burst seems to be quite nicely correlated with a slope which is 0.5. This is in the rest frame of these sources, so you need the redshift to do this game. What you can do is to add burst. This is what we tried to do in 2004. So we added other bursts that were, we mixed the sample of Sachs with the other samples of burst. And the result is that this correlation seems to be quite strong. It extends even down to very low intrinsic energies, below, let's say, something like 20 keV. And there are two bursts which are completely inconsistent with this correlation, but I don't speak that much about them. If you want, you can ask me later. And the point is that this correlation is, however, found under the hypothesis that I mentioned before, the fact that these sources emit isotropically. You might think about, there are several arguments now that might introduce what I want to say. That is the fact that, first, you know that in general, in the universe, there are several sources which are not isotropic, especially high energy sources. You have seen that the energetics that you compute, and you see here that you compute in the case of isotropy, are quite large. So you might think that gamma ray bursts are not isotropic sources, but indeed there is a jet. Therefore, the energy should be recomputed or corrected for the collimation that somehow you can think of measuring in these sources. What is the, let's say, observational point related to the presence of a jet? It's very easy, but I do it. I'm sure you are aware of that. Suppose that this is the gamma ray burst, this is the jet within which the emission happens, and you are the observer down here. What I'm saying refers to the afterglow phase. So the emission that I told you before is due to the deceleration of the outflow by the interstellar medium. So it's something which is emitting due to the deceleration of what is behind it. So the bulk currents factor is going down, but at the beginning you might imagine there are also some arguments suggesting that at the beginning of the afterglow phase the bulk currents factor is quite large, and if it is sufficiently large, you don't see, due to the beaming effect, all the surface which is emitting photon, but just a fraction of it, whose solid angle is proportional to the reverse of the square of the bulk currents factor. As you decrease, because you start to be more and more engulfed, this emission surface, this outflow starts to be more and more engulfed by the interstellar medium. As you decrease its bulk currents factor, you increase the surface from which you see the photons coming from the source, up to a point that you can imagine is particular, in which the bulk currents factor is roughly proportional to the reverse of the jet opening angle. From this moment on, even though you decrease further the velocity of the expansion of this emitting surface, you cannot see something larger than the jet opening angle. This, translated into a light curve, something observable, turns out to show, or should show, a change here, a steepening of the emission as a function of time when you reach this condition here. So by measuring, if it is possible, this characteristic time scale in the observed light curve, you can somehow infer how open is the jet of the burst. Is this prediction satisfied by the observation? I would say yes, but I will discuss later why maybe not often. Here I show you a very nice case in which you see that there is indeed a smooth transition. Before I idealized it in a very sharp way, but there is a smooth transition between a flatter decay up to here, in which you might think that the bulk current factor is larger than 1 over theta, where theta is the opening angle of the jet, to this phase in which gamma has become lower than 1 over theta. So this is what we get from the observation. This is the optical light curve of a real gamma ray burst. And by measuring the time of this steepening, which is called jet break time, you can derive an estimate of the jet opening angle. The passage from this to this is not trivial, in the sense that in this error here are hidden some model assumption that you have to do in order to transform an observable into a physical quantity. And these assumptions are not something that so weird. They are the standard assumption that the emission is the standard afterglow emission that I described before. So something produced by the deceleration of the outflow by the interstellar medium, just to say it in a general way. So if we go back to this relation, and that, as I told you, is computed assuming that all these sources are emitting isotropically, we might ask what happens if we can, for them, measure the jet opening angle through the measurement of the jet break time. The correction is 1 minus cosinus theta, and okay, we in the sense, me, Gabriele Visellini, and Davide Lazzati, when we were thinking about this, we were expecting to find something very, very special. We were expecting to find that all these points were defining a characteristic energy, which was the result found by Frail and Bloom before, that that they found just by correcting the isotropic energy for the collimation factor, that bursts were somehow collimated to a standard energy which was of the order of 10 to the 51. But in this case, considering that we have in another variable, which is the peak energy, what we find, and what we found, is this one. For those bursts, which are the black points, computed isotropically, for which we could find measurement of the jet break time, if you compute the collimation correction, and so you derive the true energetics, you end up with this steeper correlation, which is represented here and fitted to the red points. The blue points are bursts for which you do not have a secure measurement of the jet break time. And you see that, interestingly, what is changing dramatically is the scatter. Here you have a quite huge scatter of the data points. On this correlation, the scatter is, I would say, consistent with the statistical measurements on the two variables. And this is an important point. Why? Because when we found this, then we started to think about, well, this correlation seems to be a bit magic, considering how tight it is. Maybe it can have an even magic application. Let's try to think about something, and we immediately thought about supernovae. In supernovae, you know that when these sources are used for cosmological measurement of the model parameters, but they're not standard candles, strictly speaking, in the sense that they do not have all the same luminosity. What makes them standard candles is the fact that considering these, and you see it here basically, the widespread that you have at the peak of their luminosity. What makes them standard candles instead is the fact that, as you can see, there is a relation between their luminosity at peak and the rate of decay of the light curve after the peak. This is the relation that allows you to make these sources standard candles and use them to constrain the cosmological parameter. And the way is very simple. You basically use this correlation, which gives you an indication of the possible distance of these sources independent from the assumption of the cosmological model. Then you take the same distance measure from the cosmological parameters and you compare the two up to the point where the cosmological parameters are well defined in the sense that the two differ by some small amount, in the sense, okay, you make them consistent by varying the cosmological parameter. We try to do the same with gamma reverse, but before doing that, we wanted to make a very simple test. The test is, why don't we try to construct a Hubble diagram, which is the simplest, it's not a quantitative measure of any cosmological parameter, it's just a test. So let's try to see what happens if we plot the luminosity distance as a function of redshift for some supernova sample, just for comparison, and for the 15 original gamma reverse for which we had a measurement of the jet break time, and therefore of the angle. But here we made the assumption, wrong, on purpose, that they all have a unique value of the energy. As you can see, they spread out in the plane, and they are useless for any attempt to constrain the cosmological parameters that here are given by the curves, assuming different combination of omega lambda and omega matter. So what you can do, similarly to supernovae, is to introduce here, instead of assuming that all the red points, all the gamma reverse have a single unique energy, that their energy is strictly related to their peak energy. And therefore, if you make these assumptions, so you introduce the correlation that I showed you before, you end up with the points which quite well, nicely distribute in the region where you can say something about the cosmological parameters. You end up with something which is much more feasible. So this was not the introduction, but an introductory, quite historical perspective of what happened. This is something which is more updated. It's the update of the isotropic energy correlation, the one that I showed you at the beginning, up to January this year, which contains 97 gamma reversed. Out of these, people could measure the jet break time for a small fraction, only 29, now they are 30 gamma reversed, and here is where they go. So this is the updated correlation. The numbers here are important, and what I'd like you to remember is the scatter. The scatter is basically the distance of the data points with respect to the best fit line computed and then modeled with the Gaussian. So it gives you the 1 sigma dispersion of the data points around the best fit line for both the two correlations. You see that it is 0.23 for this data around the best fit correlation. It is 0.007 for this one, so it's much smaller. The other thing, but I don't want to comment about that, is that the slope of this correlation is linear, which is a nice thing to think about, because maybe it says something about the physics of these sources.
Can I ask you
Yes?
questions regarding this? So first question is that the correlated for this 29 verse is different correlation than before.
Yes.
So does it suggest that different samples gives really different results? So how different are constraints on the cosmology with different with different slope? I mean, previously it was 0.7, now it's 1. So what would be the associated differences in the cosmological parameters? And the second question related to this plot is that what about the rest of the verse that you don't measure jet break? Does it mean that they don't show jet break, or can you not put some limits on this and put on this plot where are the limits?
Yes. So the first question is, I wouldn't say that the difference in the slope of the correlation is due to any systematic.
No, before you had 21 verse, and
Yeah.
it's correct that the
No, okay.
was 0.7.
No, you're right. I missed the point. The difference is that when you compute the jet opening angle, I told you, you have to assume the standard model of the afterglow. And there are two possibilities. You might think that the gamma reverse here is within an environment in which the circumverse medium is constant, has a constant density. That's a possibility. The other possibility, which is more realistic, is the fact that given the fact that the progenitor of the gamma reverse is a very massive star, probably a Wolf-Rayet star, during its pre-explosive time, the star had lost a lot of material, then shaping the interstellar medium as a kind of density profile which goes down with a power law, which can have a typical index of -2. So the correlation that I showed you before is computed assuming that the interstellar medium has a constant density. This correlation here has a different slope simply because the assumption is that the circumstellar medium is a wind-like medium. At this level, we are not, there are no sufficient observational constraints in order to distinguish which one of these two scenarios is the best for gamma ray burst. There is only the, I would say, theoretical bias to think that the wind medium profile is the most typical environment. So the difference in the slope here, that is 1 with respect to the correlation I showed you before, is just for this. Sorry, I didn't say that.
It give you better fit?
Pardon?
Wind medium and
yes, it gives you a better fit. But considering that the points are few, I wouldn't drive any strong conclusion about that. I wouldn't mean that this correlation is distinguishing between the two possibilities. The second question, I don't know.
About this, those gamma ray bursts from the sample that you don't measure.
Yes, I will come to this. I will come to this maybe in a minute or two. But I have something to say.
Yes. So the differences between the two models, the one with constant density and the wind-like, it's quite consistent. So when you have such a tight dispersion here, are you including any dispersion, even if you take the wind-like, which is probably more favorite, you will have a huge, well, not enough for huge, but a relative spread on the whole population. So you should include that in your error bars. So probably the dispersion is gonna.
Yeah.
You're not gonna have one wind for all the clearance.
Yes, you're right. And what we could do, considering I must say that there are some measurements, both of the normalization of the wind profile and both for the circumverse medium density in the case of the constant one. So what we have done here, for those bursts, which are the majority in which you don't have this parameter, was to assume the central value of the distribution, if you are in the wind case, or if you are in the homogeneous one, for the homogeneous one, giving them an uncertainty which is consistent with the width of the distribution. It's inside, yes.
Ah, okay, great.
Yes, yes, yes. But it's a good point. It's a really good point. We lack these two measurements. We lack two. Basically, we are relying. So, given the fact that we have opened this point, we are relying in making this correction in the model on two parameters which are really uncertain. One is this one, which is difficult to measure, the density, both the type of profile and then the number. So the value of the constant medium density in the case of the constant medium, or the value of the normalization of the density profile for the wind case. And the other point, the other parameter that we are assuming is the efficiency. Because I told you at the beginning that the afterglow is what happens due to the dissipation of the energy that you didn't dissipate in the prompt phase. Okay? And the jet break is a measurement that you do in the afterglow, is a property of the afterglow. So in making this conversion from the jet break to the jet opening angle, you have to set in how much energy, how much kinetic energy you are having after the prompt phase. So how much, if you want, you dissipated with respect to the total energy, how much then is driving the expansion in the afterglow phase. And this is a value which you can assume a single value and doesn't change much. But if you put in a dispersion which goes from 0.1 to 99% in the efficiency, the things changes a lot. The values, the few values that were measured for the efficiency seems to point about a typical value which is 20% of the efficiency of dissipating energy in the prompt phase. So something like 80% roughly, okay, remains in kinetic energy for the afterglow phase.
So how many out of 29 are Swift events?
How many of the 29 are
Yeah.
Swift? I would say that they are something like 9, 10.
Right.
Yeah. All the other are pre-Swift. And for most of the pre-Swift, there is some kind of hint of the fact that this parameter, I was saying, the efficiency is of the order of 20%. And there are some hints, but you must rely or you must believe in them, of the possible measure of the constant density profile value of the density of the ISM or of the medium of the normalization of the wind. But it's really a kind of choice because the data are not so much constraining.
But the uncertainties are already in there.
Yes.
One is
Okay. So, just to show you some results, this is not interesting in terms of values, but interesting in terms of shape of these contours. These are the contours that you can obtain on the omega meter, omega lambda plane. This is the dashed lines are for 19 gamma bursts on top of the correlation corrected for the angle. This is the most recent sample, 29 gamma bursts. And here, just to show you in comparison how much we are not competitive, I put also the 156 supernovae type 1a of the sample of Rees et al. 2004 and the 68% WMAP contours of the first year. So it's clear that at this level we have so few gamma bursts that we cannot say that much about these two cosmological parameters. Even maybe we are not that much interested in constraining these two. But I think the interesting point is that, as you can see, gamma bursts are complementary with respect to the other two probes, and therefore they could be used jointly to constrain something or to say something about these parameters. The reason of the, let's say, different orientation of supernovae, WMAP, and gamma burst here is basically an effect of the dependence of the luminosity distance on redshift. So if you make this game, you can immediately realize that it's a very simple exercise that supernovae type 1a are giving these contours are oriented this way simply because their average redshift is of the order of 1 or maybe lower. When you go up in redshift, you go up this way and you become almost vertical. And then if you go to the 1000 redshift of the WMAP of the CMB, you go this way. So there is a counterclockwise rotation of the contours as a function of the redshift of the probes you're using. Yes.
What is the average redshift of the gamma bursts?
For this 19, it was 1.2, I think. For the 29, now it's about 2. Maybe something which you can try to do, but still it's a possibility, is to use or to see if gamma burst can be used to say something about the dark energy. This may be much more interesting, also because they are probing a redshift range which is not probed by any other point like, I would say, or point like a source like supernovae, for instance. And these are the results that we obtained with gamma burst. This is the original sample, the 17 sample of 2004. And you see that, well, clearly they are not still constraining anything, but they are at least excluding some part of the plate. And this is the lambda Ghirlanda model. This is for the case of an equation of state of the dark energy which is not evolving with redshift, okay, the simplest case of, for instance, a cosmological constant. This is instead the case, but not through this formula, which is not correct, in which you assume that gamma burst in which you use gamma burst to, for instance, constrain a possible expansion at first order of the equation of state of dark energy. Therefore, if you want to probe the possible evolution with redshift of dark energy. And in this, clearly in this plane, we are completely subject to the few numbers of events we do have. Even though I must say that even increasing the number of gamma bursts, maybe these contours are not closing up that much, because it might well be that the dominance of the dark energy started quite low redshift, and therefore with gamma bursts, and if you have a population of bursts which extends to very, very high redshift, this game is, I mean, the game of adding points might not result so much efficient. This plot is old. I'm sorry. I wanted to do it these days, but I didn't find. I didn't find the time. Sorry. However, you should imagine that this region here is much more populated. This was the original sample we had in 2004 compared with supernovae. And this is to tell you that gamma bursts are now populating this region here. Therefore, they are excellent, or they could be excellent probes of the cosmological models. This is the burst I showed you before to tell you that it is a real event. This is the farthest gamma burst we have. Unfortunately, for this event, which is quite young, we still do not have any measure of the jet break time. And it is very likely that we will never have a measure of jet break time for this event. In fact, to come back to your question, we were expecting to measure, or at least to excite the scientific community with this and working on gamma ray burst, and to have measurement of jet break time for every gamma ray burst that we detect. Indeed, this is not the case. The reason, I don't have a very simple explanation. I think there are many different causes, different reasons entering in this situation. Surely there is a physical reason related to the sources. Maybe there is a bit of human bias related to the fact that the typical jet break time are observed at about 1.5 days or even 8-10 days after the burst explosion. In order to measure this time when you have the break, you need to have observation before this break and far after the break. So, in a very general way, I would say that you need to observe the source, let's say 1 hour after the burst, and at least at 20 days after the burst. At 20 days, the source can be very faint. You can be very likely dominated by diminution of the host galaxy, and therefore, it's because these are made, or possibly should be made by subtracting the contribution of the host galaxy. So it's not a very simple measurement. But I think this is contributing, I would say, roughly, just guessing, at a level of 10% or 20% to the lack of jet break measurements. I would say that the most important point is that maybe we should be careful in measuring jet breaks because the jet break is a typical feature of the afterglow emission. In the prompt emission, you don't have a jet break. Okay, so how much time do I have yet left? 10 minutes. Don't lose it. So this is the simulation, but it's just propaganda to show you what would happen to the cosmological planes by having something like 150 gamma ray bursts. Okay, it's well, it's impressive, but I must say that we started with 15 and we doubled the sample of gamma ray burst with measured jet break time in 4 years. So I think we'd be retired for the time we will
So
have
what
100.
are you assuming here for the redshift distribution?
I was assuming I tried with different, I think this one is made assuming that they follow the cosmic star formation rate.
Okay, because I guess your problem is that you're not probing the era where the dark energy
Yes,
is really
you're
important.
right, you're right.
But you assume that you do that here. So you need more low redshift gamma ray
Yes, in fact. We need more low redshift gamma ray bursts for this reason, and the other reason, maybe you get it, is the fact that the correlation that I showed you is not calibrated, in the sense that in order to plot the points there, in the end you have to assume a cosmology. And so it is a circular argument if then you use this correlation to constrain the cosmological parameters. The reason is that we do not have enough low redshift gamma ray bursts to calibrate this correlation. A possible outcome or a possible solution to this problem is to leave the correlation uncalibrated, and so let's say allow it to be a different correlation in every cosmology you test, but at the expense of finding somehow larger contours on this plane. It's a detail. I mean, it's a Bayesian method that overcomes the problem that it is not calibrated. The calibration could come either with very low redshift events or with a sufficient number of gamma ray bursts in a narrow redshift range, where the cosmological assumption is not that much, it's lower than the dispersion of the correlation you have. So I want to make this point because I think it's important. What I've been telling you about the use of gamma ray bursts as cosmological probes is not just my personal idea, it's something that other people have been trying to do. So if you don't trust me, please trust them. And the interesting point is that the gamma ray burst field is populated of many correlations. I would say that there are at least 5, even 7 correlations, which maybe have something in common. Maybe one is the re-addition of the other, or so forth. But most of this correlation have been claimed to be used, or to possibly be used, as distance indicators. And these are, in my opinion, the 3 possibilities that have been proposed. One is the one that I showed you, using this correlation. The other possibility is to use this correlation in which the points are not corrected for the collimation angle. but at the expense, in my opinion, of assuming some kind of statistical extra scatter term in order to make, let's say, these points consistent with the power law. And finally, it has been also proposed to combine the other one are below this green point, to combine all the correlation together and somehow statistically weight or average out the errors. I think that considering that we are not sure that gamma ray burst can be really used to this purpose, to demonstrate the cosmological parameters, even the fact that there are many uncertainties or the scatter of this correlation is very large, for the moment I would rely on the method which at least has the less number of further assumptions. So I would choose, like in supernovae you do, a correlation which has a complete control on systematic, for which you have a complete, or you think to have a complete control on systematic effects. So I wouldn't use, for instance, this one, in which you have to assume that the dispersion of the points, the extra dispersion of points, is something that you don't know and you model with a Gaussian distribution or something like that. Even though it is appealing, if I can use this one, because I have, instead of 29, I would have 100 gamma ray bursts or something like that, and numbers would be clearly different. Okay, this is, I don't, like Lukas, I think I was thinking to have much more time than, this is a list of issues. So just I just presented you the funny thing, the funny part of this possibility to use gamma ray bursts as cosmological probes. These are all the issues instead which are related to this use of gamma ray bursts as cosmological probes. I wanted to go into the details of at least two, but I think you are tired, and if you want we can discuss if you want later, I don't know, but I don't want to
Let's discuss something.
something. Okay. So maybe the first one, which was the question of Lukas about the jet break time crisis. I told you that since we started this, since we found this correlation with the jet break time in 2004, we just doubled the sample in 4 years. So it seems, and it's a reality, that we are measuring less jet break time than what is expected, or that with respect to what we would like to do in order to add points to this correlation. The reason is, I think, due to different effects. One, I think the most dominating one, is the fact that before SWIFT, before the launch of the SWIFT satellite, which is a satellite dedicated to study gamma ray bursts in 2004, it was launched, the view of a gamma ray burst we had was something like this. This is the prompt emission, gamma ray emission scaled down to this energy band in the X-ray, and this is the afterglow emission, so the X-ray emission. As you can see, there seems to be quite good behavior with the two emission being scaled as a function of, as a power. But we were missing observation in between, basically, because you needed to the satellite, there are several observational constraints related to the fact that you needed from ground, for instance, to have the satellite giving you a refined position of the gamma ray event, and therefore you could start to observe it with a telescope, with an optical telescope. And this delay was typically of the order of a few hours. SWIFT was made to solve this, to see into this gap, in the sense that it is a satellite that whenever there is a gamma ray burst can slew within 1 minute to the position of the burst, point an optical telescope and an X-ray telescope, which are co-aligned, and look there if there is a transient event, and therefore discover the afterglow within 1 minute or so. So, the result of SWIFT, instead of confirming that if you extrapolate backward in time the afterglow to the prompt, they match each other, SWIFT showed that this is not the case. And in particular, it showed, here I make a schematic view, that typically after the prompt phase, so after the, let's say, 100 or a few 100 seconds of duration of the prompt, the emission decreases as an exponential, or very steeply in general. Then it sets into a flat phase, or shallow decaying phase, and then it goes on. The typical afterglow was, that I showed you before, in which you measure jet break time, is this emission here. Why do I tell you this? Because when you go in the optical emission, and you compare the optical emission, okay, there can be flares also on top of this, But if you compare the optical emission of the same burst, the optical emission instead seems to be, in many cases, like this, not showing this step-like function. This is what I called, generally speaking, case 1. X-ray and optical are different, but there are also cases which X-ray and optical are very similar, like this one. Why do I tell you this one, this point? Because if, and you know there are quotes for the afterglow, if the X-ray and the optical emission are due to the afterglow, I should observe a jet break. So, roughly speaking, if I don't see any break, and if, by the way, if the optical and the afterglow are due to the same emission process, they should also behave in the same way, so like this and this. It's very unlikely that an optical emission became like this and an X-ray emission became like this are produced by the same emission region, by the same population of electrons and so forth. So, the idea is that maybe the X-ray is dominated by a component which is not the afterglow. And if it is correct, you shouldn't expect to see jet break time in the X-ray. Instead, if the afterglow component is dominated by the optical, you should expect to see it. So, I can show you the examples, but I'm going to... These are two examples of case 1, optical and X-ray different. Optical and X-ray very similar, except for the first phase, which is the decaying phase, which has another origin. So what we have trying to answer this question, why we do not model, why we do not see jet break, we selected a good sample of gamma ray bursts, the R33, for which you have the optical extinction measure, so you can do things quite well. And these are a few examples. Here, according to our modeling, the X-ray, which is the green points, is dominated by a component which is not the afterglow, okay? Whereas the optical is dominated by a component which is the afterglow. So, considering that the jet break is a characteristic of the afterglow emission, you should see a break in the optical. The correlation that I showed you can predict the time of the break. The break should be observed here where we do not have points, unluckily. So here is the human, let's say, bias, the fact that nobody went so late, or maybe could not get so late observations of the burst. So a jet break should be observed, but only in the optical, but no optical data. Below you see another case in which, according to this modeling, the X-ray is dominated by the afterglow, the optical by the afterglow, and therefore a break should be observed. Again, unfortunately, the optical doesn't extend to the time when the break is predicted, but the X-ray does. And in fact, if you look to the X-ray, a possible hint of a break of something which is becoming steeper in decay here is present. So, the measure of the jet break shouldn't be, my point is that, if you want, I have the last example, which is this one. In this case, the X-ray is dominated by a non-afterglow component, the optical too. No jet break should be observed. And in fact, you see that both the X-ray, in the time when the break is expected, and the optical are not showing it. So my point is that the jet break search shouldn't be a blind search of any break you might find in the optical or X-ray. But it first should combine all the observation that you have, optical and X-ray and possibly other wavelengths. And it should be carefully done in the sense that if you have any hint of the fact that your emission component is not the afterglow, you shouldn't expect to measure a jet break. So I wouldn't conclude that the burst is not showing a jet break because it is an isotropic source. I would conclude that in that case, possibly, this component, which is not the afterglow, is dominating the emission. And I have some hints to prove that this is the case for this burst and for the other 30 that I didn't show you, and therefore that the jet break missing problem is not a problem, it's something which is related to the fact that often the emission is not afterglow.
How you put here the expected jet break time?
Through the correlation that I showed you.
Okay,
so
you just
just
point up to,
yeah,
to find it in the
bringing
correlation.
them, yes, and so the central line is when you put it on top of the line, and then you have this shaded region here, which gives you the uncertainty, I mean, which is related to the 3 sigma dispersion.
It's harder to determine jet break from X-ray.
In general, it is harder.
The scatter is much
Yes, and also because the X-ray, from this analysis that we performed, the result is that more often the jet break seems to be not afterglow emissions. So jet breaks should be searched more frequently in the optical, which is dominated by the afterglow. The X-ray, there are many indications of the fact that even at a few days after the explosion can be dominated by a component which is not the afterglow. So it's not produced by the deceleration of the outflow by the interstellar medium, but it's something different. And there are several possibilities for this.
How do you know that it's something different?
Okay.
Is it just because it doesn't have a break?
No. In this modeling, what you do is that you, for instance, here you see it better. You let the emission in every band to be composed by the afterglow emission, which is the dashed line that you see here, and by a non-afterglow emission, which is this kind of, I call it late prompt because it's made similarly to the emission related to the prompt phase. Okay, and so, for instance, in the optical, in this case, you can model somehow the emission dominated by the afterglow. But for instance, in the X-ray, this is a flare, so it is excluded. You see that it is much better dominated by a late prompt. The fact is that having contemporaneous data in the X-ray and in the optical, you must satisfy some rules about the spectrum. Okay, so here you see just the light curve, but then you have some receipt for the spectrum.
So you assume the standard synchrotron spectrum
Yes.
and extend it to X-ray band
Yes.
and compare.
Yes. So that if you want the distance in normalization between the data points here is telling you an important fact that it should be some value, it shouldn't be larger than a certain value, and this constrains which of the two components is dominating. It contributes to constraint, it's not the only thing. Oh, I will, so if I finish.
How about the wind medium?
Eh?
If you jet propagating wind medium, it's jet expansion, jet break, it's even milder.
You mean when you measure the jet break?
Yeah.
The fact is that on average in a wind medium you would expect the jet break to be at earlier times. Okay, because the density contrast is very high at the beginning and then it goes down. So you decelerate more the fireball as it enters in contact with the medium, with the contact discontinuity with the medium, whereas instead going farther to collect a mass which is with the set of Taylor solution.
But this modeling is assuming homogeneous environment?
In this case, for the afterglow, yes, we are assuming homogeneous, and therefore we are using the homogeneous case to derive the constraint on when the break is expected. But okay, yes.
Yeah, my point towards
it doesn't.
In wind medium.
It doesn't change that much because no, it doesn't. It doesn't change much because we tried that, but as I told you, the data we have are too low sampled to constrain or to distinguish between the wind medium, also independently of our modelization. If you take the standard afterglow, I would say that the parameters are too much degenerated to disentangle the wind medium from the ISM, because in a standard afterglow, you have to make the radiative emission and therefore to reproduce the light curve, you have to assume the hydrodynamic part, but also for the emission part, you have to set in epsilon, the fraction of energy going to the electrons, to the magnetic field, and they can be fixed, or they can be fixed to a partition, or they can change as function of time. Then you have the efficiency of the radiation, okay, of the radiative process, and the jet opening angle. So all these things are making you this kind of light curve in the model, in the standard afterglow, and then the density profile, either ISM or wind. Yes.
At the beginning, you said that in prompt emission, not all the negligible fraction of the energy is dissipated because of the low efficiency of the internal shock.
Yes.
So now, if you say that the X-rays, we see from this plot that the X-ray flux is orders of magnitude above the optical one. My question is, if you say that, okay, all the X-ray come from the prompt emission, and optical only sometimes go from the afterglow, does it influence the energetics? Namely, you have to dissipate much, much more in the prompt emission, in the internal shock that your model before assumed.
If you
much
think,
less in the afterglow.
yes, you're right. If you think that the X-ray emission is internal shock emission, yes, but the idea is different because it comes from the fact that very often in the X-ray you see the flares. We were speaking about this yesterday. And these flares are suggesting, or could be suggesting, the fact that the emission is not an impulsive emission due to something that lasts 100 seconds, but due to something that goes on for 10 to the 5, 10 to the 6 seconds. So the energy, the energy reservoir of the central engine is larger than what you can have from the instant or from the accretion of the very beginning phase. So the idea is that the X-ray is made the same way. It's made from late time accretion phases, and the dissipation mechanism is not necessarily the internal shock. Okay, we think it is internal shock, but there are other proposals by other people that it could be something different. The important thing is that you should have something which is able, after the accretion of the inner part of the disk, to feed another accretion phase, which can last up to 10 to the 5 seconds. And there are two papers, I had the thing to show you, but there are two papers that came out recently and that consider the work of Chevalier 1989 that showed basically this. This is the McFadden 2001, but it's more or less the same. That by fallback of material in an exploding star in which part of the core, of the material of the core, didn't get enough escape velocity to be ejected and then comes back, you can sustain, if you want, the accretion as a function of time up to very large time scale. Therefore, this is, and then there is another point that, according to their calculation, the behavior of the m dot as a function of time should be, after an initial rising or constant phase, go down as t to the minus 5 third. Okay, so this is in the case in which the emission is sustained by. So, if you want, I can convince you that it's not far from what we find because in this modelization of afterglow plus another component that we do of the light curves, both in the X-ray and in the optical, this is what we obtain. We obtain that, on average, if you want, the component 2 has a typical decay slope, which is t to the minus 5 third, which is indeed what seems to be a typical value for fallback accretion. Okay, so this is an a posteriori result which seems to favor the possibility that the emission in the X-ray, also in the optical it's possible, not only in the X-ray, but more often in the X-ray, could be due to late time accretion and dissipation much closer to the central engine with respect to the standard afterglow.
Still, you should keep the afterglow later, or not?
No, even contemporaneously. The afterglow, you do it as soon as the first shell that comes out from the central engine is decelerated. So the afterglow is contemporaneous. In fact, it's the dominance of one component with respect to the other which determines the light curve. But they are present always at the same time in every band. Did I kill you?
No.
Sorry.
We'll continue.
This is going on YouTube.
Yeah, we can continue.
Possibly there are a few observational biases. What kind of observational biases?
You had some 0.5 there in your...
Yes, but we go on for another 30 minutes. Yes, there is a debate, I would say, about observational biases. The major point is the fact that people is saying that this correlation, independently of the cosmological application or not, but the correlation that you see, for instance, between the isotropic energy and the peak energy is due to selection effects. Let me see if I go there. So we have a limited time. I will be very, okay, this is the correlation in the, that I showed you at the beginning, in the rest frame, between the isotropic energy, okay. In discussing selection effects, every correlation is okay, because if you destroy one, you have destroyed all the others. So, in the rest frame, you have this correlation. When you transform back to the observational plane, you see that there is somehow still a correlation between the observed peak energy and the fluence. Okay, people have claimed that basically in this okay, we have studied this. People were claiming, so we said let's try to see if it is correct. In this plane, there are two regions of avoidance of points, here and here. Here, the missing points seems to suggest the fact that sources cannot do that. I mean, there are no gamma bursts with an intermediate or low peak energy and a very high fluence. And this is a very likely a physical reason for this. Up here instead is where selection effects could be dominating this correlation. So, is it possible that this distribution of points I see is due simply to a cut which I have here? We have tried to study in our way, for instance, the selection effects that we can have in this plane. And I mean, when I say selection effects, I mean instrumental selection effects. Because in order to put a point here, you need to detect it with a satellite, and you need to measure somehow the redshift and the spectral properties, the peak energy and the total fluence, okay? So these are the curves for different satellites that contributed some points or part of the points in this sample. The trigger threshold, which means a point here wouldn't be detected by this satellite. A point here would be detected, okay? This is basically. It is clear that these lines here cannot reproduce this cut here, okay? So I would exclude the trigger threshold. The other possibility is that instead is what we call the spectral threshold, which means that in order to measure the peak energy of a spectrum, of a burst that you have detected, you need somehow a larger flux in the spectrum, okay? Good signal to noise, let's say. So it is more constraining with respect to this one. With this one, you need a minimum flux to detect the source. Point here, for instance, doesn't have enough flux to constrain the peak energy and some other parameters of the spectrum. So we computed these curves, they go here, and the result is that as you can see, first, they are oriented in a different way with respect to what you might imagine is the selection effect. And there is a region here, clearly, which is lacking points. So the fact that here there are no points is suggestive of the fact that this cut here, if you think about the cut, is not due to this selection effect. These are only the selection effects we could imagine about the points. Instead, down here, we clearly have a relation between the selection effects and the distribution of points, okay? But what I mean here is that this correlation is not going the same way as the selection effects might induce, and this correlation is missing point here. So if it was a selection effect, I should find a lot of points distributed here, maybe something like a uniform distribution of points up here.
Batsy is not relevant.
Pardon?
Batsy is not relevant in this figure.
It's not very?
It's not relevant in this figure, I guess.
It's not relevant?
No?
Yes, it's here.
This diagram, okay, this is fluence.
Batsy is here.
Yeah.
Okay.
So you don't need to have
you see it here,
redshift information in this
it's contributed most of the points in this region here, and its selection effect, more stringent selection effect is done here. So why there are no points here? It might be that it is the redshift which does that, but by comparing the fluences of bursts with measured and without measured redshift, we didn't find any difference in the two. So this means that bursts without measured redshift more or less follow the same correlation that you see here with bursts with redshift.
Did you try including results from integral with it?
What?
Did you try including results from integral? From the integral satellite? Did you include the integral threshold?
No, we didn't include the integral and conus wind. The reason is that in order to make these simulations, these are obtained by simulations, you have you need a model for the background of the instrument, and you need the detector response metrics. For conus, they are not public at all. For integral, maybe you can find something, but I would say that I wouldn't expect them to be much different from Bazzi and Sachs. Bazzi is very similar to conus wind in terms of geometric area, in terms of thresholds, and Sachs is not that much different from integral, at least for the high energy instrument of integral. So, and by the way, the integral points belonging to this population are, I think, 1 or 2.
Yeah, I think there was 5, I think, but I think you counted until.
And with yeah, and then with redshift maybe
Yeah.
1 or 2.
Yeah, I think 2.
So, if you want, I stop. Otherwise, I can go on.
Batteries run out.
Okay, let's thank our
No, I
speaker.
almost finished.
But we're still allowed to ask him questions, right? We had some questions in between, that's why it took slightly longer, I guess. So if there are some more questions, of course we will.
I got to take the AC, the power supply.
Yeah, I mean, yes.
I need it.
So you can think for 1 minute before the speaker will come back. The time. Okay, questions? Yes.
Why is 980425 such an outlier?
Eh. There are two. I show you the picture while I say that. Indeed, there are two outliers. One is 98,425. The other is 03,1203. The first thing they have in common, but I don't think it's a reason for them being outlier, is the fact that these are one of the first two bursts that were found in association with the supernova. This is supernova 98BW, this is supernova 2003 LW or something like that. But this doesn't seem to be the reason for them being outlier, because simply speaking, there are other two bursts here which are on top of this correlation, which do have a supernova associated too. We have tried to investigate several possibilities. One, the first idea we tried was, could that be that the environment of these two bursts is so much absorbed that we lack, because you see that their peak energy is not different from that of other gamma ray bursts, but simply we are missing a part of its flux because it is absorbed. We tried with that, with some simulations, but we end up with the fact that it could be, but you require first a large amount of scattering material around at a certain distance, and it should be only in these two bursts and not in the others. So it is a possibility, but instead the idea that I think it's a good possibility is the fact that in these two cases we simply missed part of the emission because of an instrumental effect. And this idea comes from the fact that here this burst is 060218, which is a burst detected by Swift. It's at low redshift as a supernova. And most of the emission of this burst, you see it's also here, it's, so no, sorry, it's not here, it's down here. It's at about a few tenths of keV. If Swift, simply speaking, didn't have XRT on board, this burst would have been an outlier somehow here, because you just catch, in that case, the high energy emission of the burst. You measure peak energy, which at the beginning of the burst spectrum evolves in time, is quite hard. And this seems to be the case for these two. We didn't have data, there are no data to prove this for 980425, but there are data to prove this for 031203. So it could be that its spectral evolution is quite fast, and the beginning, the end of the emission, or the central part of the emission, where most of the energy is coming out in this burst, was missed because we didn't have an X-ray telescope that was looking to that burst at that time. So we just catch the first
usually
one.
how do you define EP? You define EP for integrated spectrum?
Yes, yes. All these bursts, the spectral shape, the peak energy and the isotropic energy is measured by taking the duration of the burst, integrating the
Just
emission over the
integrate whole
duration, and
duration.
taking an average spectrum, let's say.
Can the same effect move some points from the correlation to out of correlation?
I wouldn't say, you mean taking a point and bringing it the other way? No, because for all the others, you have a peak energy which is well constrained, and you have also the low energy extension. You can exclude that you are measuring just the initial part of the emission. For O3 to O3, really, if you look to the light curve, you have the initial part of the emission, the spectrum is hard, and then you have a gap, you don't have observations. If the spectrum is evolving as, for instance, in 06 or 218, most of the emission is coming out later when you don't have observations. So, if you apply this and you take the same law, okay, you move this point roughly here, both. So they can go nicely on this, but by assuming only that their evolution is the one of 08 or 218, or sorry, 06 or 218.
How about just these guys are just local population and being possibly being and his collaborator argument some another population
Yes,
happening nearby.
Yes, another possibility is that all these two outliers, this burst here, which is not represented of 06 or 218, and 0329, I don't remember the name, and the other, I mean, there are 5 or 6. They are all at low redshift. They all have a quite low luminosity, clearly with these two outliers, but the other are at the bottom of the distribution of the energetics or luminosity, more or less. And so they argued that they could have a different origin. They could be a different type of explosion, not, let's say, not that much relativistic as standard gamma ray burst. Or the other possibility, not that much collimated as standard gamma ray burst, so wider explosions.
More questions? Yes, sir. Do you have any questions? You work in this business.
I don't know.
Do you believe in the correlations?
I mean, there was really a lot of interest back in 2004, and maybe you can say that the interest has gone down a little bit.
Yes.
So why is that?
Yeah, that's a good question. So, why is that?
There were many people that really jumped onto this bandwagon in the start, but now they...
Yes, you're right. I think surely one thing is the fact that we expected, everybody was expecting to fill this plot with hundreds of gamma ray bursts. So the fact that after the launch of Swift, the jet brakes didn't come out, I think made people less confident about this. That's one possibility. I must say that we can discuss about that, but I mean, the selection effects are discussed a lot about this correlation here. For this correlation, up to now, I wouldn't say that there are clear outliers. There is a claim for one outlier, okay, which is here, but it's a strange burst. It has an efficiency which is 99%. It has a density which is 10 to the minus 4, okay, if measured from the data. So, I mean, as I said before, the degenerative are there. So, I don't know. The possibility is that it's not that much filled with points, but my point instead is, apart from the cosmological application, this correlation is derived under some hypothesis that might be wrong, that gamma ray bursts have a jet. If you don't believe in this correlation, you should then say that all gamma ray bursts are isotropic sources. So the point goes back to the fact that we should deal with these energetics. So it's not a problem of the correlation itself or whatever, but if we don't trust in this, and I'm open to that, let's go back, therefore, to the isotropic model of gamma ray bursts, which have their own difficulties in explaining many observational effects.
So
You're not putting this on YouTube because
So these points are all long bursts.
this point?
Are all long bursts.
Yes. Yes.
Short bursts are slightly shifted.
Short burst, to my knowledge, there is no clear measurement of jet break time for short bursts. There are
Yes.
4 bursts.
But we
which
can
are
put the constraint always.
Yes, but okay. Also, the short burst with the measured peak are 4, and the result is that short bursts have an average isotropic energy which is a factor of 10 or something lower than that of long bursts. So the 4 bursts with short, with measured redshift, measured peak energy, goes somehow here. Okay, considering the isotropic energy. You don't have for these 4 any measurement of the break time to put them here if they go here, or farther out if they have the same opening angle of long gamma bursts. So short bursts are still, I don't know where they go. I only know that for long bursts, for the isotropic energy, they are here. They are outlier of this correlation, I would say. But there are 4, so maybe not.
Do you have any good theoretical reasons for explanations for this kind of correlations?
Not yet, not definitely. Well, this one, there are some proposal for this one, for using the isotropic energy. Then it's not different for this one. You translate it for the collimation corrected one. The models that has been proposed are of 2 types, in my opinion. One is the one which I think is more interesting is the radiative explanation that was proposed by several authors, Thomson, Jars, and Rees, for instance, saying that simply this slope of this correlation is 0.5, right? This is a kind of characteristic temperature. This is a luminosity. Okay, so it can be explained if you think that the emission in gamma ray burst is thermal, is something which has a black body origin. And with really few passages, they indeed can reproduce the slope of this correlation. Okay, if under the hypothesis, theoretical hypothesis, that gamma ray bursts have a black body spectrum. In general, gamma ray bursts do not show a black body spectrum, but possibly this is true when you consider the integrated emission of the burst. When you take slices of the burst emission as a function of time, also Felix showed this, you see that there can be a possibility that the spectrum has a black body shape with maybe some non-thermal contribution at the tail of the spectrum at very low and very high energies. So it's a possibility which is intriguing. Why not? But instead, what intrigues me quite a lot, if it is correct, is that this is 0.6, so don't trust it. But when you use the wind correlation, I told you, and you correct for the angles, it becomes linear. Okay, and the linear correlation is simply saying in this plane is somehow suggesting that the number of photons is constant, and it corresponds to 10 to the 57 photons, which is a number which is not by chance, I think.
Is the same number of neutrons in neutron star.
Well, at least one coincidence.
Whatever this tells you.
And it's Lorentz invariance, the other thing.
Okay. Thank you, Giancarlo.